Support vector machines. SVM was first introduced by Webnik and has been a very effective method for regression, classification, and a general pattern recognition. It is considered a good classifier because of its high generalization performance without the need to add a prior knowledge, even when the dimension of the input space is very high. It is considered a good classifier because of its high generalization performance without the need to add a prior knowledge, even when the dimension of the input space is very high. The aim of SVM is to find the best classification function to distinguish between members of the two classes in the training data. The metrics for the concept of the best classification function can be realized geometrically for a linearly separable dataset. A linear classification function corresponds to a separating hyperplane f of x that passes through the middle of the two classes, separating the two. Once this function is determined, new data instance xn can be classified by simply testing the sign of the function f of xn. Xn belongs to the positive class if f of xn is greater than 0. Because there are many such linear hyperplanes, SVM guarantee that the best such function is found by maximizing the margin between the two classes. Intuitively, the margin is defined as the amount of space or separation between the two classes as defined by the hyperplane. Geometrically, the margin corresponds to the shortest distance between the closest data points to a point on the hyperplane. Having this geometric definition allows us to explore how to maximize the margin so that even though there are an infinite number of hyperplanes, only a few qualify as the solution to SVM to ensure that the maximum margin hyperplanes are actually found. An SVM classifier attempts to maximize the following function with respect to W, arrow, and B. That is, LP is equals to 1/2 times the double norm of the vector W minus sigma summing for index I from 1 to t of the term alpha I times yi times the term W times xi plus b. Then plus another summation summing for again the index I starting from 1 to t of the term alpha I, where t is the number of training examples, and alpha I, where alpha I is indexed from 1 to 3 until t, are non-negative numbers such that the derivatives of LP with respect to alpha I are 0, alpha I are the Lagrange multipliers, and LP is called Lagrangian. In this equation, the vectors W, wave, W arrow, and the constant B define the hyperplane. A learning machine such as the SVM can be modeled as a function class based on some parameters alpha. Different function classes can have different capacity in learning, which is represented by a parameter h, known as the VC dimension. The VC dimension measures the maximum number of training examples where the function classes can still be used to learn effectively by obtaining zero error rates on the training data. For any assignment of class labels on those points, it can be proven that the actual error on the future data is bounded by a sum of two terms. The first term is the training error, and the second term, if proportional, to the square root of the VC dimension h. Thus, if we can minimize h, we can minimize the future error as long as we also minimize the training error. SVM can be easily extended to perform numerical calculations. And here we discuss two such extensions to extend SVM to perform regression analysis, where the goal is to produce a linear function that can approximate that target function. Careful consideration goes into the choice of the error models in support vector regression, or SVR. The error is defined to be 0 when the differences between actual and the predicted values are within an epsilon amount, and otherwise the epsilon insensitive error will grow linearly. The support vectors can then be learned through the minimization of the Lagrangian. An advantage of support vector regression is reported to be its insensitivity to outliers. One of the initial drawbacks of SVM is its computational inefficiency. However, this problem is being solved with great success. One approach is to break a large optimization problem into a series of smaller problems, where each problem only involves a couple of carefully chosen variables so that the optimization can be done efficiently. The process iterates until all the decomposed optimization problems are solved successfully. A more recent approach is to consider the problem of learning an SVM as that of finding an approximate minima enclosing ball of a set of instances.